In this presentation, we meet contingency tables and the chi-square test. Think of it as a lie detector for categories. Are they actually related, or are we just seeing patterns in random noise? By the end, you should be able to answer the classic question. Is this association real, or is statistics trolling me again? This slide is just about recognizing when the chi-square table party starts. If you have two categorical variables and you can count how many people land in each combo, like gender by opinion or teacher by pass or fail, that's a contingency table. When your data looks like a bingo card of counts, the chi-square test is usually nearby, quietly sharpening its claws. This is the basic stage on which the chi-square drama happens. Every cell has a count, every row and column has a total. And the grand total is just everyone in the study. Once you can read this table, you can start asking, are these patterns real or just randomness wearing a fancy grid? The null is always the boring story. No relationship, nothing to see here. The alternative is the spicy story. Something is going on between these variables. The chi-square test is basically asking, are these differences big enough to blame more than random chance? When we say two categorical variables are dependent or associated, we just mean knowing one of them helps you guess the other with better precision. If every row has the same pattern of percentages, there is no help at all. That's independence. If the percentages change from row to row, there is some association. You can also think about dependence from conditional probability perspective. Does knowing one's blood type change our idea about the probability of left-handedness? If that's the case, blood type and handedness are associated. For example, if the overall chance of being left-handed is about 10%, but among people with blood type O, the chance of being left-handed is, say, 15%, then blood type and handedness are associated. Because knowing the blood type changes your idea of the probability of being left-handed. If the probabilities stay the same no matter which blood type you look at, then the variables are independent. Note that correlation is a similar idea of moving together, but it is a specific numerical measure for quantitative variables like height and weight. For categorical variables like gender and opinion, or blood type and handedness, we don't talk about correlation or lack of correlation, we just talk about association or independence. The idea is simple. If the variables are really independent, the expected count must be such that probability of male and 4 is equal the probability of male times the probability of 4, which is the basic definition of independence for events. For the chi-square test to be valid, all expected counts must be at least 5. If your expected counts are tiny, the chi-square test starts to complain. This statistic follows chi-square distribution with the mentioned degrees of freedom and thus is called the chi-square statistic. It is a global measure for how far away the observations deviate from independence. Since all the pieces are positive, chi-square statistic can never be negative and we would reject the null for sufficiently large values of it. That is why the rejection region always lies in the right tail of the chi-square curve. This is the chi-square recipe card. First write the boring and the spicy hypotheses. Pick alpha. Build your expected counts. Cook up chi-square. And then ask, is this value so big that independence looks unrealistic? The final answer should always be in pro language. We either reject the null or do not have enough evidence to reject the null. Here are the raw counts from our survey, a little 2 by 3 contingency table. One variable lives in the rows, one in the columns, and every cell is a head count. The big question is, does this pattern look like what we'd expect? If gender and opinion had nothing to do with each other. On the next slide, we'll build the ideal table under independence and see how far reality wanders from that ideal. Notice how the expected table is perfectly balanced. Both rows have the same pattern because independence says, gender should not change the opinion percentages. The observed table is close but not identical. The chi-square test will now measure whether those gaps between observed and expected are small random wiggles or big enough to scream association. Our chi-square value is way smaller than the cutoff of about 6. So the differences between observed and expected look like normal sampling noise. In plain English, in this sample, opinion and gender do not seem to have a strong association. Chi-square is great at saying, hey, something is going on here. But it never explains the human reasons behind the data. That part still needs curiosity, empathy, and actual conversations. Stats tells you where to look, not what to think.